First of all, good morning to everybody. Thank you for inviting me. I feel honored to participate in this this conference and with all these expert panelists and so on. So let me start here, which is the introduction to nuclear weapon technology and the types of nuclear weapons. I'm going to divide this presentation in 4 parts. First, part 1 is putting things in the proper context. Next part is the nuclear difference, and then what are nuclear weapons? And then what are nuclear weapon effects? And some of this will overlap with the excellent presentation that we had earlier. Putting things in a proper context. So this is actually a figure where you can see fission happening, where the neutron comes in, smashes the nucleus, and then gives off two or three other neutrons, which you kind of see in yellow there. Okay, let's start here, which is a presentation by at the Bulletin of Atomic Scientists announcing the hands of the doomsday clock in 2020. And this is Rachel Bronson, who's the president of the Bulletin.
Inside the 2 minutes is no more urgent than the preceding period. Citizens around the world should rightfully echo the words of climate activist Greta Thunberg and ask, how dare you? With this in mind, I'd like to now ask Jerry Brown, Mary Robinson, and Ban Ki-moon to approach the clock to reveal the 2020 time. Today, the Bulletin of the Atomic Scientists moves the hands of the doomsday clock. It is 100 seconds to midnight.
So this is where we are right now. And this is where you see the minutes to doomsday. And so the doomsday clock is kind of a measure of how close we are to doomsday, to a very serious catastrophic situation, either with the planet due to climate change, which is happening right now, or one which may occur in the future if we don't stop it, which is nuclear weapon use. We will focus on the nuclear weapon concerns, of course, but I will touch on sometimes climate change as well, because the two are also interconnected. Sharon Squazzoni, who's a speaker coming after us in next panel, next exciting panel, said at this event, which you can find on the Bulletin of Atomic Scientists website, that right now with serious problems with arms control, which I'm sure we're going to get into in this conference, it's too dangerous to kind of sleepwalk through these times. And we needed a renewed effort in arms control. There's been a real issue over the past few years with, US getting out of treaties and other issues, which I'm sure we're going to discuss. Okay, so this is a kind of a graph which shows you the number of nuclear weapons over time, and it's showing all the different countries. So you see the UK, China, France, Israel, Pakistan, India, and North Korea. It's plotted on a kind of unusual scale, which increases in a factor of 10. And why that's useful is because you see all the countries at once, and you can see, what is happening with the nuclear weapon arsenal for all the different countries. What we see is that Russia and US, the number of nuclear weapons, so you see that Russia is in kind of gray and US is in black. You see that the number of nuclear weapons has been decreasing over the years. This always reminds me, when I look at this graph, it just reminds me of the situation with COVID-19. When you see that some countries are plateauing, which is not necessarily good. We really want to decrease all these numbers as fast as we can so that we don't run into a situation where nuclear weapons will be used, whether it's on purpose or whether it's by accident. So even though the countries have plateaued, it just means that they have still a lot of nuclear weapons. And we do see, for example, that North Korea is increasing its nuclear weapon stockpile. So Russia and the US each have about 900 nuclear weapons right now, which are on high alert and could be used at any moment. Why are we concerned here is, again, putting it in the proper context, is that tensions are growing between the different countries. We see that, for example, there's a potential conflict between China and India, India, Pakistan, US and Russia, of course, and US and China potentially, and other countries as well. These are all nuclear powers, so we're very, very concerned about this. The other thing is that countries are modernizing nuclear weapon delivery systems, as well as, you know, decreasing nuclear weapons, but also modernizing nuclear weapons. And so, for example, the US has shown interest in developing maybe low yield nuclear weapons, and appears to be interested in new nuclear weapons. So there's a serious concern here from that point of view. Plus, in 2020, we know there's sustained interest in fissile material production that Gustavo talked about, fissile materials, uranium-235 and plutonium-239. So, for example, we know that Iran is developing, you know, enriching more material, and is going back on some of the promises with the Iran deal from 2015. Plus, there's a fading memory. You know, it's 70 plus years since Hiroshima and Nagasaki, and people have to be reminded. And I'm so glad to hear that in this conference there will be testimony from survivor of the atomic bombs. But my fear is always that the memory is fading. And also there's a possible interest now in nuclear testing, with the United States accusing both Russia and China of possibly having conducted very low yield nuclear tests. And the fear is that, you know, with the moratorium that's existed since the 1990s, that there will be, you know, that potentially go back to using doing nuclear testing. So that's where we are now. So now let's talk about the nuclear difference. And this is, Gustavo touched on some of this already, and I don't want to be too repetitive. But let me just talk about from a slightly different perspective. This might seem funny, but let's start with a kind of a riddle. What has more energy, TNT or chocolate chip cookies? And it's going to be relevant for the whole presentation. What has more energy, TNT or chocolate chip cookies? Well, you know, the way I'm phrasing the question, so probably chocolate chip cookies has more energy density than TNT, and that is true. It is 8 times more energy density in chocolate chip cookies than in TNT. And you can see here on this graph a comparison between the different materials that have energy in them. TNT, chocolate chip cookies, is 8 compared to a TNT of 1, and coal is 10. So then the question might be, why don't we explode when we eat chocolate chip cookies? The reason why we don't explode when we eat chocolate chip cookies is because we use the energy very sparingly over time. So now we have to kind of put in the mindset of nuclear reactors, use the same source of fuel, which is fission, but it's used slowly over time, over years, whereas in a nuclear bomb or chemical explosives, it's used in a very quick amount of time. So then we're really talking about what's called power, which is the energy released per unit time. So TNT then has higher power than chocolate chip cookies. It releases its energy very quickly. And the same is true with nuclear weapons. So just to put that in the proper context, if coal is 10 centimeters, and I suppose on your computer screens from the previous screen, coal is about 10 centimeters big, then if you put uranium on that scale, it will reach to the orbit of the International Space Station. It's 30 million times, it would be 30 million on that scale compared to 10 on the previous scale. So it's a huge difference between nuclear energy and chemical energy. And then recall what Gustavo said, which is that 1 uranium pellet is about 360 pounds of coal or 160 kilograms of coal. So the difference is that reactors or coal use the energy slowly, whereas chemical explosives, you know, it explodes and it releases energy very quickly. Nuclear explosives, or NEM, as I call nuclear explosive materials, use energy just in the blink of an eye. So here you see this kind of essence of the nuclear difference, which is that the energy release is slow for coal and for power reactors, so that the energy can be used safely, but it's fast for high explosives and fast for nuclear explosive materials or nuclear weapons. The other huge difference of why there is really the essence of the nuclear difference is that a single fission is 1,000,000 times more energetic than any chemical interaction. So you can kind of think of it this way. They use the energy unit of electron volts. And when you're thinking about chemical energy, you're thinking about 1 to 100 electron volts. Whereas when you're talking about nuclear physics or fission itself, you're talking about hundreds of millions of electron volts. So that's really the main essence, that's the difference. The other thing is that with nuclear, if you configure your material, your nuclear material in a certain way, you can initiate a fission chain reaction, and that leads to many, many fission interactions. So not only do you have is a fission interaction very, very energetic, but also you can induce it in a way that you can produce many, many fissions. So this is what I call the nuclear difference. On the left panel, what you see is 1 kilogram of TNT exploding. So this is a screenshot from a YouTube video where somebody blew up 1 kilogram TNT. On the right side, you see 1 kilogram of uranium-235 exploding. And this is basically what it was for Hiroshima with this massive, massive explosion. So there's a tremendous energy density difference between chemical explosives and nuclear explosives. Even though we talk about the science, I think it's important to always be aware of the unspeakable horror that happened in Hiroshima and Nagasaki. And for me, pictures are less powerful than seeing the paintings and so on by survivors. So this was created by Masato Yamashita. A girl has died in the Ekogawa riverbed with no one there to help her. So part 3. So we're going right along here. What are nuclear weapons? Well, let's start here. Nuclear explosive materials, as Gustavo already mentioned, it really starts with uranium-235. And uranium-235 is an isotope or a component of uranium that you would have if you dig in the ground and you would look at any material. And it's mined. And so if you analyze the material, if you just look at dirt or you look at seawater or whatever you want to analyze, you will find that 0.7% of that material will be uranium-235, and the rest will be uranium-238. Now, as Gustavo mentioned, uranium-235 is used for is for fuel in reactors. It's also a nuclear explosive material that you could use for a bomb. And uranium-238, which is whatever is left from the 0.7%, 99.3%, you can use that in a reactor. You can place it in a reactor and produce plutonium-239, which is your other nuclear explosive material of concern. So I don't want to go to this in too much detail here. The source of the energy that we have is fission. This normally happens because of a decay called spontaneous fission. But basically, you see in this picture here, a neutron comes in, splits a nucleus, and releases 2 to 3 neutrons. These neutrons then can initiate further fission interactions. This kind of decay where you have spontaneous fission, which is when a nucleus like uranium-235 spontaneously decays, is very, very rare. But here you can see you don't have to wait for a long time. You can actually induce fission by having a neutron hit an isotope like uranium-235, having it split, that produces 2 or 3 more neutrons, and that's how you can initiate further fission interactions. So here what you see is what's happening in this chain reaction. And this is similar to the graph that Gustavo showed. what you see is you see a neutron comes in here at the top and then hits an atom. This splits, produces 2 or 3 more neutrons. Here I'm showing 2 neutrons, then finds another U-235 and another U-235, splits that, and then produces 2 more, and so on and so on and so on. So what you can see here is that the fissions per generation increases very rapidly. What you see is that you first have 2, then you have 4, then you have 8, then you have 16, then 32. And then for your 80th generation, and some of you who have a chemistry background might recognize this number, you get 6 times 10 to the 23 splittings. That's equivalent to the atomic mass of uranium in grams. So after 80 generations, you have 235 grams of U-235 being used up in the process. Then you have an 81st generation, 470 grams being used, and 82nd generation, you have basically 1 kilogram being used up. And this is the essence of why I showed this graph here, 1 kilogram of TNT being used up. Okay. In a bomb, this happens very, very fast. In a nuclear reactor, this happens slowly, as I discussed before. So this is just to do kind of a quick back of the envelope calculation here, taking those numbers to kind of get a sense of how extreme really nuclear weapons are and a kind of sense of the scale that we're talking about. So one fission in itself is actually very, very little TNT. If you would do a comparison between one fission, it would be 7 times 10 to the minus 15. So that would be 0.00001, 15 times grams of TNT. So a very small amount. But because you have so many fissions, 10 to the 24 fissions in 2 to the exponent 80 in 82 generations, that's equivalent to 18 kilotons of TNT. So that's an enormous amount. And it's always important to get a sense and just sit back and think about how much is 18 kilotons TNT. And you see here that it's 18,000 times 1,000 or 18 million kilograms of TNT, which is an enormous explosion. The other thing you have to remember is that the production of energy happens very, very fast. It's 82 generations from here before, 82 generations from here before, and 10 to the minus 8 seconds for the neutron that's being emitted to find another atom to split. And so that's 10 to the minus 8 seconds, or it's called a shake. And so you have 82 or 100 times 10 to the minus 8, which is 10 to the minus 6, which is basically 1 microsecond. So I said in the blink of the eye before, that energy is actually used in much faster than a blink of the eye. In terms of the mass that's fissioned, as I said before, it's 4 times 235 grams or 1 kilogram of U-235. So you see the essence of these nuclear weapons are that they produce a lot of energy, they produce it very fast, and very little materials actually used in it, very little fissile materials used in it. So what are nuclear weapons? It's a rapid assembly of nuclear explosive materials, NEM, into configuration that will sustain a fast neutron chain reaction. At least 1 neutron is released per fission that produces another fission, and you need higher than critical mass, or what's called supercritical mass, or MC, to produce this. It must cause a fission rather than being captured or escape from the configuration. And to produce a nuclear explosion, the fast neutrons from each generation of fissions must produce more fast neutrons in the next generation. So everything has to do with managing the neutrons and making sure that they don't escape from the configuration, from the assembly. A useful way to think about this is in terms of mousetraps. And I know that sounds strange, but if you have mousetraps, you can kind of picture them like this, where you're placing these mousetraps side by side. And each of these ping pong balls that you place in the mousetrap represent the neutrons that are being released. So 2 or 3 neutrons, and in this case, it's 2 neutrons. When one of these ping pong balls hits the mousetraps, what happens is the mousetraps get unclamped and these little balls fly off. And this is basically what happens in a nuclear weapon. If you understand this, you really understand a lot about how nuclear weapons work. You also know from this that it's very important to have those traps very close together, or that the unit U-235 density has to be high. What does that mean? That means that the enrichment has to be high of the material. So there's no U-238s in between. Remember that I said that 0.7% of the uranium that you have, which is dig in the ground, is going to be uranium-235. The rest is going to be uranium-238. And so in this case, the U-238 kind of plays a spectator part. So you want to have this little U-238 that get in the way. So that means that you want to enrich the U-235 to as high as possible. So here I'm showing what happens. So this is essentially how nuclear weapons work. And it's kind of in this crude picture, it's actually how it works. The picture here of the plexiglass that you see here is also what you would use in nuclear weapons. Not plexiglass, but you would use other kinds of reflectors to make sure that the neutrons go back into the critical mass so that you can sustain the nuclear chain reactions. Now, there's really two types of nuclear weapons that you have to kind of think about. These are the older version of nuclear weapons. The first is the gun type design. And this is the type of design that was used on the Japanese city of Hiroshima. And in this case, what you do is you assemble, because remember, assembling the critical mass is the main point. You assemble, let's say, half a critical mass with another half of critical mass together to reach one point. And you do this as fast as possible. So basically shoot one part into another part to assemble it and to start the fast chain reaction. In actual fact, in the case of Little Boy, the bomb that was dropped in Hiroshima, it was they used much more than half a critical mass and slammed it together. And it was a very unsafe bomb in that sense. What is used but as I say here, it's very simple in design. Even a high school kid could do it, is what Luis Alvarez, who was a Nobel Prize winner in physics some time ago, and I think worked on the Manhattan Project, he said that even a high school kid could do this. It's just a matter of having access to highly enriched material, but enriched to high percentages to be used in this type of weapon. The other type is, and only uranium-235 can be used for this type of bomb, not plutonium, as I'll discuss a little later. For plutonium, what you have to do is you have to use high explosives to basically compress the fissile material, and that could be highly enriched uranium, or that could be plutonium of different types. And basically you're compressing it into a supercritical state. And so you're imploding it, and this implosion causes it to be compressed into a little ball, or different configurations, and this will initiate the explosive chain reaction. So in the case of plutonium, the issue is that you have a lot of spontaneous fissions, and so you have a lot of neutrons. And so because you have this problem, you can't use it in a gun-type bomb, where, as I'll touch on a little, I think in the next slide, where you need to have basically 1 millisecond of no neutrons, no spontaneous neutrons or no extra neutrons that come from the environment to have this actually work. So in this case, it's through compression that you change the critical mass. So normally, as you can kind of imagine here, you have this spherical shell, and the spherical shell itself is not at critical mass. So in that sense, it's also much safer than and I use safer between quotes, safer than a gun-type design. And then you compress it using high explosives. And if you compress it by a factor of 2, it results in a reduction of this critical mass by a factor of 4, which has a big effect. And then on top of this, kind of think about this, reflectors, we had the plexiglass, you can put reflectors to make sure that those neutrons that will escape go back into the fissile material. You don't lose those. And then you can also use heavy materials as tampers to reflect and hold the core long enough together so that when it explodes or when it implodes, you know, there's no escaping of neutrons. There's two ways to a bomb. So I already mentioned the gun type bomb and the implosion type bomb. And here at the bottom scale here, this is one of these BBC dad moments. I'm sorry about this. You have at the bottom here, you have the nuclear fuel cycle that we discussed, that as Gustavo discussed earlier. And then, and here you see the enrichment here, and here at the top of this part, I'm dividing the slide into two parts. The non-peaceful side, or the nuclear weapons side, and the peaceful side, which is the nuclear fuel cycle, which Gustavo excellently discussed in the previous presentation. One way is through enrichment. So using the exact same kind of equipment that you would use to enrich material for fuel, for a reactor, you could use exactly that same equipment and use it to enrich it further to greater than, say, 90% uranium-235. And you could use that for a gun type bomb or for an implosion type bomb. And then after reprocessing, as Gustavo mentioned, you can separate the plutonium, and you can use that plutonium and use that in a bomb, as well as the highly enriched uranium. So there's really two ways here for producing a bomb. And you see here the vulnerability of the fuel cycle in this way. And that is why we, people in the non-proliferation community are so concerned about the Iranian program and making sure as they have a right to peaceful use of nuclear materials, but the concern is that it could be used for alternate purposes, non-peaceful purposes. So properties important for nuclear weapons are fissile material reactivity, really the critical mass, the configuration, how it's been designed, and the quantity of material to ensure that a chain reaction can occur. Ease of handling, you have to make sure that it's not very radioactive and it doesn't produce too much heat. So one issue is I'll touch on in a little bit, talking about reactor grade plutonium. So this is the plutonium that's out of a power reactor, produces a lot of heat and a lot of radioactivity, and it's more difficult to manufacture a nuclear weapon bomb, but it can still be used to make a bomb. The other problem, as I already mentioned, is the neutron background, which has to be low, so the spontaneous fission rate has to be low. But there's generally two ways of making a fission bomb assembly: the gun type bomb and implosion type design. So again, even though we speak of the science, which is interesting, we always have to keep in mind to bring us back to the context, which is the horror that happened during the bombings of Hiroshima and Nagasaki. Here we see people wanting water gathered around the cisterns. This is from Unagi Akira. I found them just as they were when they drank and died. My heart aches as I apply the red color. Can non-state actors build nuclear weapons? Well, the barrier is getting the fissile materials. In the 1960s, the government asked two students that just graduated from grad school, actually, to design a gun type bomb. With no knowledge of nuclear weapons, they actually designed an implosion type bomb, which is much more sophisticated. Remember what Luis Alvarez said. A Princeton University undergrad designed an implosion weapon as a senior paper. The labs were tasked a while ago, and it was actually Vice President Biden who asked for this asked for this to be done, as far as I remember, to build a gun type bomb with commercially available material without breaking any laws, except for obtaining the fissile material. So this really tells you what the concern here is, which is obtaining the fissile material. And they were able to do it in a few months. So as I said, plutonium really can't be used in a gun type design. You need a neutronless millisecond, but plutonium naturally gives off many neutrons, 100,000 neutrons per second per kilogram. So it's really impossible for a few kilograms is what you would need to have of fissile material of plutonium. Impossible to get a neutron-free millisecond. So you really need to use the implosion method instead. So this shows you kind of a chart from the NRDC, Natural Resource Defense Council, an estimate, and this is a very good estimate on how much material you would need to have, how much fissile material you would need for weapons-grade plutonium and for highly enriched uranium to make a nuclear weapon as a function of the yield. So here you can see the yield, 1 kiloton, and that is already a big explosion. Always keep in mind what a kiloton actually is, because we just use easily kilotons, megatons, and so on, but always keep in mind what an incredible big explosion that actually is. And here it shows you that for low technical capability, if they were able to have 3 kilograms of weapons-grade plutonium, which you could produce in a reactor, then it would produce a yield of 1 kiloton. For a high technical capability country, you could produce with only 1 kilogram of plutonium, 1 kiloton TNT. And the reason why I want to emphasize this is that the mass needed is significantly less than what the IEA calls a significant quantity, which, for example, for a weapons-grade plutonium would be something like 8 kilograms. But as you see here, you can have much less material and produce a bomb. Of course, this does not take, this is critical mass. This does not take into account machining losses and all that kind of stuff. But it's definitely true that it matters. The technical capability of the country matters in terms of how they could utilize small amounts of fissile material. And for example, in 2008, as part of the 6-party talks, North Korea declared that 2 kilograms of plutonium were used for the 2006 tests. That gives you a sense of how much material that was used. Of course, that was a very low yield test. And in 2012, the Soviet test result was declassified, which that they used. Of course, they are very sophisticated in developing nuclear weapons. They have a lot of experience. That they used 0.8 kilograms plutonium to produce 1.6 kilotons, or 2 kilograms plutonium to produce 5.8 kilotons. And the former deputy DG of the IEA, Oli Heinonen, called for really the plutonium significant quantity to be decreased significantly from where it is now because of this concern. Now let's compare reactor-grade plutonium. So with reactor-grade plutonium, so this is plutonium that's been not produced specifically for nuclear weapons. This is not weapon-grade plutonium. This is plutonium out of a power reactor. So this is, you know, generally some countries feel that this material, you can't make a nuclear weapon out of it, but actually you can. So there are some barriers. So the radioactivity is significantly higher in terms of curies per kilogram. So don't worry about curies, it's just a unit of radioactivity. For weapon-grade plutonium, it's 3, and for reactor-grade plutonium, it's 10. The heat is higher, so you have to be able to contend with the heat. And the neutrons emitted are higher, significantly higher. But these are all barriers that you can get around. The neutron background is important in nuclear explosion because it can influence when the explosive chain reaction starts. And the concern here is something called pre-detonation, so that the bomb will, you know, for example, if you use plutonium in a gun type design, as it becomes assembled, it'll just start to disintegrate before the time it's been able to get to a critical mass. So you really can't produce a bomb. But there's ways around that and ways you can deal with it, at least in terms of plutonium, in terms of reactor-grade plutonium. So it's been widely cited that a key problem is, you know, that radioactivity and heat and neutrons are a big problem for reactor-grade plutonium. However, the yield will be less for reactor-grade plutonium, but it doesn't mean you get 0 yield. It could still produce a bomb with reactor-grade plutonium. And here are some quotes or some useful quotes on this. So a military useful first-generation nuclear explosive using reactor-grade plutonium can be designed to produce a nuclear yield in the multi-kiloton range. So we're not talking about a very large yield, but again, when we're talking about nuclear weapons, you always have to keep in mind, what does 1 kiloton mean? It's really extremely big explosion. And if non-state actors would get access to materials like this, it would be a deep concern. So with the reactor grade plutonium, the yield would be at least 1 kiloton and likely much higher. And this is a statement from one of the important reports. A potential proliferating state or subnational group using designs and technologies no more sophisticated than those using first-generation nuclear weapons could build a nuclear weapon from reactor-grade plutonium that would have an assured reliable yield of 1 or a few kilotons, and probably even higher. And this was from a US report on nuclear weapons. So the US has actually has detonated bombs with reactor-grade plutonium. So it is a concern. Okay, so this is another image. Sasaki drew this image of a girl at a window on the second floor of a burning house. Sasaki remembers the girl crying for help. I can never forget. Modern nuclear weapons are a little bit different. You use boosted nuclear weapons, and in this case, you add a small amount of deuterium-tritium gas is added to the core of the nuclear weapon. So this would be the fission, so that you kind of think of a bomb in 2 stages, as I'll talk about in the next bullet. It's called the primary and the secondary, and the primary is the fission bomb. And what you can do is you can have a certain amount of deuterium-tritium gas. Deuterium-tritium is basically hydrogen gas, a different type of hydrogen gas. Deuterium is a non-radioactive gas. And tritium is a radioactive gas, but if you add a little bit of that to the core of the nuclear weapons, then you can greatly increase the efficiency and hence the yield of the bomb. And this also means it's secured from pre-detonation that I discussed earlier. Excuse me. And you can also have staged nuclear weapons, such as the hydrogen bomb or the thermonuclear bomb. And in this case, what you do is you have a primary and a secondary. And here I'm kind of showing this picture here when you have the warhead itself in kind of cone shape here. You have the bomb. So this is the reentry body of the warhead. The primary, which is the fission bomb, and then the secondary, which is the fusion bomb, primarily the fusion bomb. And so the idea is that you have a boosted design where you produce a lot of heat, and this heat interacts with the secondary, which has the fusion bomb, and the temperatures increase so high that fusion reaction starts, and this leads to further fissions as you produce more neutrons through the fission reaction. And then, for example, you can have a uranium mantle around here, and the neutrons that you produce through fusion, because that's really what you're doing with fusion, will interact with, for example, the uranium mantle, which will produce more fissions. And so you start to produce a very, very, very powerful bomb producing very, very large yields. So now we're talking about megaton bombs. So for example, bombs in the nuclear arsenal, which right now exists, which is the largest bomb in the United States, that is in the United States arsenal, which is the B-83 gravity bomb, which is 1.2 megatons TNT. Now, again, it's important to put this in the proper context. 1.2 megatons TNT is put into a format after years and years and decades of optimizing these designs, that the mass of these weapons would be several hundred kilograms. So if you then want to think in terms of coming back to the chocolate chip cookies, if you want to think about it in terms of that scale, now we're talking about a 100 kilogram bomb, a couple of 100 kilogram bomb that can be put on missiles, producing a yield of 1.2 megatons or 1 million megatons. This then would mean that you have an energy density of 1 million. compared to the chocolate chip cookies, which was 8. So it's an intense amount of energy density that you have in these bombs, and an immense amount of destruction. Okay, so where are we now? So there's 2 ways to bomb, as we discussed. We have been building a tremendous amount of nuclear weapons, as we talked about, and we're modernizing nuclear weapons. And I showed this slide, which was from a movie called Deep Impact. Of course, it has nothing to do with nuclear weapons, but in terms of the doomsday, Putin showed in 2018, I believe it was, you know, many different types of new nuclear weapons of concern. One of them is called, nuclear powered, with nuclear weapons aboard, cruise missile, which can basically fly forever, which is a deep concern with this type of weapon. We've already seen several accidents with it. And for example, this picture here I'm kind of showing is this fear over this nuclear powered or you know, with nuclear weapons on board, autonomous torpedo, which Project Poseidon, I think it's called, that Russia is threatening the world with. And then of course you have US modern weapons. This is part 4, and I'll rush this a little bit. Summary of nuclear weapon effects. After the bombings, of course, there were 135,000 deaths in Hiroshima and Nagasaki. This is the upper end. Nagasaki, 65,000 deaths, 135,000 deaths. We're close to that with COVID-19 here in the United States. So it's important to kind of see that context here. And what happens is, as Gustavo mentioned, you produce a lot of fission products that are radioactive, and you produce a lot of devastation that's caused by the pressure wave, the blast wave, the firestorm, and the incredible radioactivity. After the bombing, it didn't end. There was continued testing until the moratorium. I said in a tweet, I think it was a couple of days ago when I was making up this presentation, the bombings of Hiroshima and Nagasaki should have been the end of it all, but instead it was the beginning, because as you know, there was a lot of nuclear testing, and because of the nuclear testing, a lot of this was not done underground. It took a strong movement from the public to force the tests to be conducted underground. But the damage has a lot of the damage has already been done. Physicians project that some 2.4 million people worldwide will eventually die from cancers due to atmospheric nuclear tests conducted between 1945 and 1980, equal to a force of 29,000 Hiroshima bombs. That comes from IPPNW, International Commission to investigate the health and environmental effects of nuclear weapons production, and was done with the help of Arjun Makhijani, a very respected physicist in this field. And you can scrutinize those numbers by yourself by going to the book called Radioactive Heaven and Earth, which is freely available from the IEER website. I touched on this at the beginning. Dr. Hilda Hien, she's the president of the Republic of the Marshall Islands, declared a national climate crisis in, I think it was October 2019, as she said, a toxic dump of radioactive materials. So basically what happened after testing on the island of Runit, a lot of the nuclear materials, radioactive materials were kind of dumped in this dome, in this kind of shallow dome. And the fear is that with climate change and as the water level is creeping up, her fear is that that material will go into the water. So in terms of the effects of the bomb, and I'm going to want to wrap it up here as quickly as possible because I want to provide some time for questions. In terms of the effects of the bomb, there's the blast wave, the energy from the shock wave. which energy in compression, the thermal, this is kind of how the energy, so when we talk about 10 kilotons or 18 kilotons or whatever, this is how the energy is compartmentalized or partitioned. 50% is blast wave energy, so this is the energy that would do a lot of damage from the winds and so on that you would create. 35% is thermal energy released, this is electromagnetic radiation, this is heat and so on. And then 50% is the nuclear radiation. The initial, some of the many issues, and this is a long lecture in its own, is the initial fires that were started by the thermal radiation, which combined and produced these super fires, which caused a lot of devastations, which happened about 20 minutes after the explosion. You kind of think about this amazing fireball that happened produces these light particles that each have their own little effect. And it's kind of like having a magnifying glass when you're trying to produce fire. You're focusing all that energy, but in this case, you don't need to focus it. It just started grass burning and so on. And so that's really the deep concern with these kinds of effects from nuclear weapons. There's been a resurgence of the nuclear winter. Imagine a skirmish in Kashmir escalating, which right now seems very apropos, due to poor communication, misunderstanding, panic, and fear. Perhaps this time we won't be so lucky. Alan Roebuck and Owen Brian Toon have done recent studies. This was 2009, but they've continued these important studies by imagining what would happen if you have a very small exchange of nuclear weapons, 100 Hiroshima-type weapons between India and Pakistan, which again is only 0.03% of nuclear weapons that exist in the world. The effects are devastating. 20 million people would lose their lives, but that is not all. And this is the reference there, which you can see. It will have a very dramatic effect, which is massive amount of smoke and soot from fires, because of the fires would rise into the upper atmosphere, which would block the sun. And this is the concept of nuclear winter. Sunlight would be reflected back into space. It would lead to rapid cooling of the global surface temperature of the Earth. This would mean the collapse of basic life-sustaining ecosystems. Now, this is the end of my presentation, but it's such a terrible thing to end on this. And here you can see the global climate change. This is what would happen. This is the temperature anomaly. This rapid decrease in temperature, which would have a dramatic effect on the planet. This would lead to increase in price of food, mass starvation, hoarding by countries that have the funds. So of course, my deep concern with what will happen with COVID-19 with the vaccinations. I'm always fearful that hoarding will happen by the countries that have the money. We'll have disease, war, competition for food. According to the IPPNW, with the International Physicians for the Prevention of Nuclear War, they've done several estimates of this, and 2 billion people, with a B, 2 billion people would be at risk. So this is just a summary slide. Nuclear weapons use fissile materials like uranium-235 and plutonium-239, and you can refer to the nuclear fuel cycle in Gustavo's previous lecture. Reactor-grade plutonium can be used to make nuclear weapons, but plutonium cannot be used in a gun-type design. And this really gets to the point of how important it is to control these fissile materials and minimize the use of these materials in reactors and other applications whenever it's possible. Modern weapons use boosted designs and thermonuclear weapons. And the last part is that the effects of nuclear weapons go much further than we ever imagined. Nuclear weapons don't only affect nuclear weapon states, as we see between India and nuclear weapon possessing countries, but all countries, as we see the climate effect for nuclear weapon use. Even a small exchange that's localized to, for example, India and Pakistan, will affect everyone. So it's everyone's responsibility to deal with this. So for this, I end and I'm open for questions.